to make sure everybody feels comfortable. All right. If there's no questions, we'll dive in. So this is our last video lab. It's been quite a year. We've done quite a few of these video labs now, and we are at the end of the video labs. Not the end of our labs, of course, but the end of our video labs, which is the part 2 of the analysis of vitamin C. Finally, we actually can take a look at, I mentioned this, the medical challenge of seafaring without the proper vitamin C on board and the scurvy that can result. We talked about that last week. Again, I want to say this week video lab, last video lab, not the last lab. Next week, we're going to do a sim lab, again, a simulation lab on electrochemistry. And then the week after, in 2 weeks, we've got our at-home lab for the term. We need alum. So I'm just going to keep trying to tease you with some pictures and videos that I've taken. I'm done with my at-home lab. I have my results. Remember, my goal was in 1 week to grow a baseball-sized single crystal of alum. So we're going to find out in 2 weeks whether or not I was able to do that. So you need alum. Here is 1.9 ounces. You're going to find out that if you are really interested in engaging with this lab, more alum would be better. So how big of crystals, how pure of crystals, how many experiments that you choose to do, it's going to be a little bit open-ended. And so we'll talk about it, but I will say it's pretty fun. So I want to give everybody that heads up. And also, regardless of the day that you meet, that week, that lab week, so not next Monday, but the Monday after, you should kind of mentally think that that is when your lab is or when it should start. This isn't going to be a great lab to do together in person. It's going to be far better to utilize your lab meeting times to check in and ask questions of your lab instructor. But time is a huge element in this lab. And if you are with me on a Friday lab, you won't want to wait till Friday to start this. And as much as we like meeting with the groups of the people we know, there's not going to be very much to do. It's going to be like, are you boiling water? I'm boiling water. Okay, we're boiling water. So there's not going to be a lot of problem solving per se, but you're going to be able to do a lot of little experiments if you want to, and checking in would be a useful thing. So I just wanted to give everyone kind of the mindset of that April 12th lab is going to be something we do on our own. Very simple as far as the procedure. Understanding the science of crystal growth is enormously complicated. So there's a lot to learn here, but not a huge time constraint except little bits over the week. So you're going to need a tablespoon or just a spoon. And truthfully here, because we're going for saturated solutions, and I'll give you some tips on how to make sure you have a saturated solution, and we can use some colligative properties to our advantage there. So it can be a tablespoon, but really you just want 1 spoon. I just used a plastic spoon the entire time as just I remembered 2, plastic spoons or 3 plastic spoons to be consistent. A ruler doesn't have to be metric. Just make sure that you're prepared for your unit conversions if you have an imperial ruler. But I would recommend a metric ruler with as many sig figs as you can. We're measuring the size of our crystal. So the more accuracy that your measurement tool has, the more accuracy you can report. That's what sig figs are. You're going to need string or dental floss. I've already showed you some pictures. I tried both. I like dental floss a lot better for this experiment. It worked for my entire trying to grow a baseball-sized crystal in a week experiment. The dental floss held up. So I recommend that if you've got it. Hopefully you do. And then a container to really commit to growing your crystal in. The size is important here. You're going to want to suspend your seed crystal into saturated solution. The bigger the jar that you have, the more saturated solution you need, i.e. if you're going to try to beat my crystal size, you're probably going to need more than 1.9 ounces of alum, because every time the crystal grows, you need a bigger jar. And with a bigger jar, you need more saturated solution. So I would make sure that you think that you really want a jar for the size of the crystal that you want. The size of the crystal that you're looking at right here, about quarter size, and they're very pure crystals, which is also something that we can attempt to do, is to grow something extremely clear, extremely pure, with facets that represent the crystal lattice. And so again, talk about that in 2 weeks, but make sure you have a container that is not too big, but not too small. So picture the size of the crystal that you want to grow and make it just big enough to hold that. Any questions on this? Because by next week, hopefully everybody will have their alum in their house, even though next week's electrochemistry. We want to make sure we're ready for this.
One thing to suggest too, you need distilled water. So that might be something that if you're ready to start the problem, to make sure you have some distilled water available.
Yeah, so you can definitely, we always use DI water, especially when we want to control salts and making sure that we have pure crystal lattices. These crystals here were not grown with that, just for kind of for equity purposes. So again, this is good. 99 cents, you can get a gallon of DI water. I have a couple of jars always in my closet for at-home science experiments, but then I also can say the lab will function without that, but you're going to have to ask yourself, what can those ions that are in the water, in the tap water, do to the alum that we have, the purity of it? And also, can they do anything to disrupt the purity or the size or the scale of my crystal growth? So it will work without DI water, but I do agree that if we're looking for the best lab experience that you can, the best crystals you can grow, DI water will be superior. It's not very expensive. At every grocery store, deionized water should be available. Any other questions? So we talked about this last week. Remember that when we lack ascorbic acid in our bodies, we can cause a disease called scurvy, which can be reversed with simply adding 10 milligrams a day of ascorbic acid. And the first controlled experiment done, or one of the first recorded in history, was in 1747 by Professor James Lind, who discovered that a small amount of fruit daily to a sailor could prevent these really terrible deaths that were occurring to sailors. So we talked about that, and then we just standardized a solution, our secondary standard, and we didn't have much to do with vitamin C of ascorbic acid. So today is the payoff day, or this week is the payoff week, and we're going to take a look now with our secondary standard that we know the concentration exactly. We're going to use that and do a type of titration called a back titration to determine how much ascorbic acid, how much vitamin C was actually there. So this is going to be in the video. Here's a bit of data that you're going to want to take away from the package. So this is the supplement that says it has 1,000 milligrams of vitamin C, which is ascorbic acid, and zinc ascorbate, which is a buffer system. It has 1,000 milligrams, or 1,667% of your daily value, because again, you don't need that much to be healthy, but they're just giving you plenty of extra. And they're giving you 1,000 milligrams in an 8.9 gram total sample. So if we have 1,000 milligrams, we have 1 gram of ascorbic acid, a vitamin C total, divided by the total sample mass would be the percent of vitamin C we would expect in our package. Then what we're going to do is we're going to take a small sample of this vitamin C dietary supplement, and we're going to see if our technique using our secondary standard that we standardized last week can confirm the percentage of ascorbic acid in our dietary supplement. So if we were doing this in person, you would all be encouraged to bring in whatever you want from home, and we could do this not only with fruit juices, but everybody's favorite emergency vitamin C, or any of those kinds of things. But since I just had to choose one that was in my cupboard, and I had this emergency. So this is the reaction that we're going to be doing this week. It's going to be very similar to last week. So if you felt really comfortable with the reactions that we were doing, this should seem very similar, but see what we're adding in. So now we're going to do a back titration. And the back titration is defined as a titration in which you add intentionally excess of a reagent, and then you titrate the excess. And then when you know what the excess was, then you can know what the missing element is. And so that's a back titration, using an excess amount of reactant and then titrating whatever is excess to find out something, some other analyte's concentration. So we're going to use the same primary standard, the same container of primary standard. So the concentration that we determined for our primary standard iodate last week, we're going to be using that value this week. Remember, this is a part 2, a continuation, and we've saved all of our reagents. And it will generate an excess amount of iodide, 3 moles of it in our solution. That is the excess. So the generation of our excess is the first step. Then we are going to have automatically, without doing anything, some ascorbic acid we put in there from our emergency. Hopefully there's some in there. And it's going to react with some of that iodide. And it's going to react in this 1-to-1 relationship to make 2 moles of iodine. Oh, I'm sorry, this is iodine, this is iodide. Oh, I'm all mixed up today. And it's going to do this oxidation reduction reaction and reduce the ascorbic acid to this reduced species here. And so that is, we don't have an endpoint, an indicator to know exactly how much of that reaction happened. It just goes on in our reaction vessel. And so then we take that reaction vessel with our ascorbic acid, some of which has been reduced, and we use that secondary standard, the concentration of which we determined last week. So if you're showing up here this week and you didn't do last week's lab, you're going to want to catch up because this is going to be necessary. But so you'll do a titration until your endpoint. That's when the blue color becomes colorless because of the starch complex like we observed last week, the same endpoint. And then what we can determine from that is we'll know how much excess we put in, and that's the blue line, and we'll know how much we titrated, that's the green line. And when we subtract those two, as you see on this equation here, that's how we can determine the moles of iodine that are reduced by our ascorbic acid. And so then we can use mole ratios all the way around to determine how much ascorbic acid was there. So this is what the setup is going to look like, of course, in the video. In our burette, we have our sodium thiosulfate, the concentration of which was determined last week. So that's where you're going to get that information. In our reaction flask, you're going to have 25.00 mils of our primary standard, which is potassium iodate. And so that also was determined last week. Remember, we were aiming for, I think, 0.1 molar, but we wanted to take the exact mass and determine the exact molarity. We're going to add, the instructions say 0.250 grams of vitamin C. When I was doing this experiment live, 0.250, the endpoint was reached way too quickly. It's still pretty quick this week, but that's why I tripled the amount of my sample. This would be something that you would do in the lab if you found that your endpoint was reached too quickly and you couldn't articulate exactly the final and initial volumes well enough to understand what the concentration is. You can just put more of your sample in, and that'll expand that delta V in your titration. So I do recommend, making sure that while you read instructions like this, you understand that certain instructions can be flexible. And then we're going to add about 1 gram of potassium iodide, about 5 mils of sulfuric acid, that's 0.5 molar sulfuric acid, and about 2 mils of starch. Just one word about safety, like we talked about last week, we're using 0.5 molar sulfuric acid, we're using it. 2 weeks ago, we used 12 molar and we had this conversation about safety, but I really want to emphasize that often accidents happen after you go from something that is very dangerous to something that seems less dangerous, and then people kind of relax. And that's when the accidents happen and people get hurt. And so I try to recommend, I try to remind people after we have a lab in which we had a really dangerous reagent to not relax safety because it feels safer relative. That doesn't necessarily mean that half molar sulfuric acid when spilled on your clothes isn't going to ruin your shirt or hurt your skin if you don't rinse it off, which is the second point. If you spill any of these chemicals on your skin, you want to make sure you rinse them extensively, like way longer than you think is normal or necessary. And while you're doing that, get some help. And then these salts, that's from last week, but if you're using any salts like potassium iodate or sodium thiosulfate, they're irritants. And so you'd want to make sure that even though they're solid and it doesn't seem as hazardous, those can be the most hazardous things to deal with in the lab. And then also whenever we're dealing with both oxidizing and reducing agents, the reaction of those two things can be exothermic. And when you mix in any kind of organics with that, you can have very exothermic reactions, fires, explosions. And so whenever you're dealing with both oxidizing and reducing agents, you're going to want to make sure you read the labels because they're going to tell you what you can put in and where. And then when we're dealing with acid-base waste, we'll always just neutralize it to a pH of 7, which will just make salt water, and that allows us to pour it down the sink and limit how much waste we're sending out to the stock room. And again, if you're saying, hey, this isn't an actual face-to-face lab, yeah, but the writing is definitely on the wall that we are coming back to face-to-face as soon as possible. And so we are going to be responsible for thinking like experimental chemists and thinking in a laboratory mind. So make sure that you're considering waste always and never pouring anything down the sink in a lab. All right, so the first thing that we're going to do is crush up our supplement with a mortar and pestle. That instruction is there because I mentioned that people can bring in their own supplements. This supplement comes powdered, which is I put this in red. You're not going to see me crushing it up, but I wanted to point out what a mortar and pestle are. I think we've seen this, maybe we haven't been able to name it, but this is a tool that we use in the laboratory to carefully crush things up in a way that's pure and keeps all of our, it keeps all of the powder together and doesn't absorb it. The main thing about a mortar and pestle is the ceramics it's made out of has a really, really fine lattice. And so it doesn't hold a lot of the material because you don't want every time you crush up a sample to be transferring the last 9 samples that you crushed up in your mortar and pestle. So that's what it is. That's what it's used for, but you won't see it today because the sample was powdered. So we're going to add about 0.850 grams of our supplement into an Erlenmeyer flask. It doesn't have to be exactly 0.850 grams, but we should always record the exact mass, right? So that's going to be really important once we're doing our final math and finding out what the percent of our ascorbic acid is in our over-the-counter supplement. We need to know exactly how much we put in. So while we can have a round number, the most important thing is getting those exact digits from the balance. So to that flask, we're going to add 40 mils of sulfuric acid, half molar, which will dissolve the solid. And then we'll be adding some sodium bicarbonate solid, which will neutralize the remaining acid. So we're just trying to get a neutral solution in which we've dissolved our supplement. And then finally, we're going to pipette 25.00 mils. And remember, those 2 extra digits come from the fact that we're going to use a volumetric pipette. And the volumetric pipette, when the meniscus is right on this line, will dispense 25 with 2 decimal points. So make sure you have those digits in your, those sig figs in your records. Remember that the balance gives a lot of sig figs. It's normally in volumes that we lose our sig figs. So because we have 4 sig figs here, you might have 4 sig figs in the answer, but you got to make sure that you carefully track all of your measurements. So 25 mils, the solution concentration was determined from your notes last week. And then we're going to be adding these about 1 gram of potassium iodide, 5 mils of 0.5 molar sulfuric acid, about 0.1 gram of sodium bicarbonate, and around 2 mils of starch. So what does the word about mean in this context when I'm giving these instructions?
that you're trying to reach that, but you might reach another thing and you have to alter the exact value you added.
So it's tricky here, right? Because some things, right, I'm telling you, get this exact mass, but if it's slightly off, just record the exact mass, right? And so that usually I will tell you mass out 0.850 grams. But then if you get 0.852 grams, record it as 0.852 grams. Don't record it as 0.850 grams. Often you'll get some uncertainty margin, so plus or minus 0.005 grams. So you know what your range can be, but you'll always record exactly. But when I use the word about, it means it doesn't matter. It's going to normally be an excess, and it doesn't need to be exactly there. You need to just have around that amount. So whenever I say at about 1 gram of something, you should always record your exact data. But there, if I have 1.1 gram, I'm not worried about it. And I'm going to move through those measurements much faster if I know that there are a reagent that is brought to it, the reaction in excess. So that's just something to keep in mind. And then we're going to titrate that sample with our sodium thiosulfate that we standardized last week until the endpoint. So what is the endpoint we should observe this week? Does anybody remember? It's the same endpoint from the video last week. Did it turn pink? What was the endpoint? What was the endpoint that we observed last week?
Wasn't it clear?
That's right. It went from blue to clear. This might seem like a trivial point, but in a titration, it's truly everything. And also, how quickly your endpoint is reached dictates how slowly. You should always go very slowly as you do your titration and you approach your endpoint. But some endpoints are a little bit more finicky than others. Some require more stirring. With this endpoint, because you have this complex, a lot of stirring I noticed is necessary to make sure that you can see it really well. That doesn't mean that I don't overshoot endpoints, and that's something that for you to examine as you watch the video and determine how well you think that it's being done. But you always want to know what your endpoint is before you start the titration. So here's one more picture. That's what the titration setup is going to look like. We'll start with our primary standard in the flask, 25 mils exactly. Our sample about 0.850 grams, about 1 gram, 5 mils, and 2 mils of the following reagents. Remember, iodine is going to be formed. I2 will be formed automatically in the flask. And because the ascorbic acid is there, reaction 1 and 2 are going to happen automatically right away. And some of the iodine that we produce will be consumed by the ascorbic acid. The remaining we will titrate out with our sodium thiosulfate and figure out how much ascorbic acid had to have been there with back titration calculations. So here's what one will look like. Here's just an example, and then I'm going to throw some example data at you and just walk through what it looks like before we go today. So here is our burette. We have our first reaction. That just happens automatically, right? We set up our reaction with our acid and our Ki and our primary standard, our iodate, and then this happens. And then this happens as well. So we have done nothing but created our sample. And now that the iodine that we created in reaction 1, some of which is reduces some I2, is a reducing agent, is oxidized to this oxidized species over here. And that's happening before our titration begins. And the question is, how much of our I2, how much of our iodine was taken away, and i.e. how much ascorbic acid was there in the beginning. And so now we're going to do that titration. So we're going to titrate the rest of our existing iodine that's in our solution, which is unknown to us, with our sodium thiosulfate in a 2-to-1 ratio until we reach that colorless endpoint. So I want to point out, just so that it's clear, I have the word colorless here because eventually, if you go all the way, this is colorless based on our our starch complex, but we're going to have an excess of iodine by definition of a back titration. We are going to generate more iodine than we have ascorbic acid by definition. If we put all of the things in and it turned colorless, you would say, well, I have to add more sample, which is what happened, right? Because it went too quickly. So this would go colorless, but there is some excess I2, which is why it starts blue. And so it's going to stay blue until we titrate the excess with our secondary standard. Then we see the endpoint, which was pointed out, is when it goes from blue to colorless. And so then we know that our titration is over. So if we say that the starting volume is 13.55 mils, so get that estimated second digit, even though I'm using my cartoon over here, remember that you want that second digit on the burette. And then if we do the titration and the final is 22.05 mils, again with that estimated digit, then of course we can subtract them. And once again, we are thinking about sig figs and maintaining the two sig figs the two decimal points, because with adding and subtracting, you're looking at the least number of decimal points, not the number of sig figs. So we need 2 decimal points. So we're including that 0. So that's important to remember. All right, and so we have this huge data table to put information into. And so I just wanted to walk through it, and then I'm going to show you the math, and then we'll call it a day. But I want to put on the video, on the record, where all of this data comes from. So mass of the sample, that is our vitamin C. You're going to get that data right from the lab. It should be about 0.85. The volume of the potassium iodate, you're going to get using the volumetric pipette. Don't forget those two extra decimal points that we get from the volumetric pipette. And then you can use the concentration of that potassium iodate from last week that we calculated when we made the solution to know how many moles are generated from 25 mils of said solution. So that data is going to be very similar from last week. Then again, continuing from last week, we can take that moles of iodate and reaction 1 from the previous slide and use the mole ratio to find out how much iodine we've generated. Then we're going to get the initial reading of the burette. You always have to do that in a titration. It is devastating to forget this one step. Face-to-face, it happens. So try to keep in mind that we can rewind here, but can't rewind always in real life. And if you do a titration without the initial reading of the burette, then you can't do anything and you absolutely have to start again. Okay, going down, the final burette reading also is going to be in the video after we reach the endpoint. Make sure you collect it. And then the volume of the thiosulfate titrant that we added is just our delta V. The volume is a state function. And so initial minus final is how we get delta V. So just the initial volume minus the final volume. And then we know the volume of the thiosulfate that we standardized last week. We have that concentration in our information in our lab manual already. So we use that concentration from last week and the volume that we just added. And we know how many moles of thiosulfate that we've added to get to our endpoint. So using the mole ratio then from reaction 3 on the previous slide, where we're seeing the thiosulfate react with the I2 until it's colorless and make iodide, we can use that mole ratio to say how much I2 was reduced from the thiosulfate in the titration. Then, because we know how much I2 we generated, that was on the previous slide going down this table, but on this table. And now we know how many moles of I2 were consumed by the thiosulfate during the titration. If we subtract those things, we can get the moles of I2. I skipped one. Oh no, that's right. And so then we can find the moles that are there in the sample. So this is the moles of the I2 that were reacted with our ascorbic acid. The difference between the total that we put in, the excess, minus our titration is the moles that had to have reacted with our ascorbic acid. And so then when we have the moles of I2 that react and the mole ratio from reaction 2, that middle reaction, we can find out the moles of ascorbic acid that are in our sample. Then using the molar mass of 6 carbons, 8 hydrogens, and 6 oxygens, the molar mass of ascorbic acid, we can find the mass that was in our sample from the moles. And then if we divide that mass from the problem we just did from the molar mass, divided by the sample mass, that was the thing that we first collected from the video, how much? Around 0.850 grams. We divide those two things and multiply by 100. We can get the percent of ascorbic acid in our sample. And then we can relate that to our calculated percent ascorbic acid on our packaging, which was 1,000 milligrams in 8.9 grams of sample. So whatever that percentage ends up being, how well does our percentage relate to that percentage? That's our question. So one more time, this is reaction 1 that's generating the excess. This is reaction 3, which is that back titration of then removing the excess so that we can then calculate reaction 2, that invisible reaction in which ascorbic acid is reacting with our iodine to make our iodide. So let's walk through the math here with the equations, of course. So we put in 25 mils. I'm missing a 0 here. My apologies. I should have that. 1 extra 0 there because of the 2 decimal points from the volumetric pipette. But we add 0.025 liters, and it's about 0.0100 moles per liter of our primary standard from last week. So we multiply that and we get 0.250 times 10 to the negative 4 moles of iodate. And so if we take that and we go with the mole ratio, we know how much iodate we put in based on the volume and the concentration. And so then we can find, using this 1-to-3 relationship, the moles of I2 that we generated. So we'll just use the mole ratio there. And now we've done our titration. So once we've done that, we've generated our excess. We go ahead and we do our titration of our sample. And we find that 8.50 liters, that was from the above math before I went through that table, came from right here, 8.50 mils. So we do our titration, we get the volume added, and that's when we plug that in. So 0.00850 liters of our thiosulfate, our secondary standard from last week, times its concentration. So we did that standardization. So let's say our concentration is 0.09381 mole per liter. Then we would have 7.97 times 10 to the negative 4 moles of thiosulfate that we titrated in. And next, we're going to use the mole ratio here, which is 1-to-2. And so then if we know how many moles that we put in, we can find how many moles of I2 that it must have reacted with, how many it must have consumed in that reaction by the mole ratio of 1-to-2. And then we find that we have 3.99 times 10 to the negative 4 moles of I2 that were reduced by our thiosulfate. So we've determined our excess amount of moles of I2, and we know how much were consumed in our back titration. So remember, these are the 3 steps. So we have our excess, the green is the titration that we do, and we're looking for purple. How much went invisibly reacted? And it's this simple. We generate 7.50 times 10 to the negative 4 moles of iodine. We subtract out what we know we used in the titration, and we get what must have been consumed. 3.51 times 10 to the negative 4 moles of iodine must have been consumed by the ascorbic acid. One more mole ratio, which is the easiest of all of them. We have 3.51 times 10 to the negative 4 moles, 1-to-1 mole ratio, and we get 3.51 times 10 to the negative 4 moles of ascorbic acid. Then we go to our periodic table and we go 6 carbons, 8 hydrogens, and 6 oxygens is about 176.12 grams per mole. So when we multiply our moles that we know that we must have had in our reaction vessel before the titration began by the molar mass, we get 0.0618 grams of ascorbic acid. And if we had exactly 0.850 grams of sample that we did our titration to, we could then divide those two numbers, 0.0618 grams of ascorbic acid by 0.850 grams of sample times 100, and we get something like 7.9 to 7%. And so depending on what we calculated, the package purported to have in it, we can make that relationship known and see what the error is, either error with their packaging process, which is probably unlikely, or error with our methodology somewhere on the line. So the post lab, you're going to need to know what the average concentration of the sodium thiosulfate was from last week. I have belabored this point long enough. And the post lab is going to even tell you before you get started, what was that? So that's one of your points there. Here's that table. Again, you can't even fit it all. It's very long. There's 3 trials that you're going to do total. But if you follow what I've just previously prescribed, I think that it will be no problem. And then you're going to be looking for the goal after that table is what is that average percent of ascorbic acid in our sample. So once you are able to calculate the 3 trials, you can take an average and answer question 3. And then we're going to have some conceptual questions about what happens here if the primary standard in question 4 was not completely dried. What would the effect of our estimation of our sodium thiosulfates concentration be? And then you are going to continue this down with questions 5 and 6, and then say if then that had a bad secondary standard solution concentration, what would that do continuously with our other calculations? And so it gets you into the mindset of these equations, because there is some complicated math here today. None of the individual steps are hard or new. I think we can all see, oh, molar mass, I know that. Concentration, molarity, I understand that. But when you put it all together, it's a pretty big ask. So make sure that you're prepared with questions for your instructors if you have them when you join your labs this week. So let's analyze our analyte ascorbic acid. Do I have any questions? None? Well, okay. I think it's a good lab. I'm glad that everybody here was able to get a head start on it. So enjoy your labs this week. And then again, make sure you're getting your alum in your house. Some deionized water, also a good idea. Floss or string, and some sort of glass container to put it all together in. Sound good? Enjoy your lecture today, and I will see you next week.
All right. Thank you, Michael.